Hello everyone, my name is Kaushik and today we will be understanding the hottest topic these days in the automotive world, that is Automotive Ethernet. The agenda for this session is mainly to understand what is Automotive Ethernet, what are the different application areas of Automotive Ethernet, and we will also try to understand the Ethernet frame format by relating it to the different OSI layers involved. So it is going to be a little long and detailed video, so please do follow me till the end. I will make sure that you will not be disappointed. So let's start the session. Why did our automotive world needed Ethernet? We already have CAN, LIN, etc. But still we saw the need for automotive Ethernet. This is because of new application areas like transferring of large software with low production cost, high data bandwidth, real-time data exchange, and moving from signal-based to service-based communication. If we compare the existing protocols like CAN or LIN with Ethernet, we see that the Ethernet is 10 times faster and is very flexible. The application areas of automotive Ethernet is very vast. Here I have tried to summarize different application areas and I have mapped it to applicable OSI layers. Layer 1 and 2, which is physical and data link layers, are common for all the applications. Applicability and configurations of layer 3 onwards are based on different use cases. For example, if I take SOMEIP, network layer has IP configurations, transport layer has either TCP or UDP configurations, and layer 5 to 7 will be pure SOMEIP configurations. Similarly, we have other applications like audio video transfer, time synchronization, network management, diagnostics, calibration and measurement, etc. Before we jump to understanding each layers in detail, let us first try to understand how does a Ethernet frame format looks like and what fields does it contain. IEEE 802.3 gives the standard Ethernet frame format. There are other IEEE standards which are derived from this base format as well. First field is called the preamble, which is of 7 bytes containing alternating zeros and ones. This field indicates all the nodes that there is a frame which is going to start. Also helps the sender node to establish bit synchronization. Second field is called SFD, that is start frame delimiter. It is of 1 byte and is used to indicate the start of frame. Last 2 bits of this frame is set to 1 1 to indicate the end of SFD and marks the beginning of the frame. Preamble and start frame delimiter fields are added or processed by the physical layer and thus it is called physical layer header. This physical layer header is of 8 bytes in length, but sometimes few places you can also see that the start frame delimiter is not specifically shown in the Ethernet frame format and it is part of the preamble, which is described as 8 bytes, and the start frame delimiter will then be the last byte of preamble in this case. The third field is the 6 bytes of destination MAC address, which is the MAC address of the receiver node for which the data is destined. Fourth field is 6 bytes of source MAC address, which is the MAC address of the sender node which sends the data. Fifth field is 2 bytes of length or type. This field can act as either length or type of Ethernet frame. If it is a normal Ethernet frame, which means if we are communicating from the data link layer, then this field represents the length of the payload. But if it is beyond the data link layer, that is, if layer 3 or layer 4 is involved, then this field represents the type of Ethernet message. Type of Ethernet frame can be anything. For example, if it is a IP4 protocol, then this field will contain the value 0x0800. There are a lot of such type of Ethernet frames available. To know more about it, you can find the link which is given in the description below. These three fields are called the Ethernet header, which is of 14 bytes. Sixth field is the data field. Size of this field is not fixed and can vary depending on how long the data it contains. But the maximum length it can hold is 1500 bytes and minimum length it must hold is 46 bytes. The minimum length of data field is specified to 46 bytes because Ethernet uses CSMA bar CD, which is the method used for access control and to deal with collisions. So, to detect the collisions efficiently with this method, it requires 72 bytes of data in the Ethernet frame. So we remove the length of other fields which we discussed so far. The data field must have minimum 46 bytes of data. Next we have 1500 bytes as maximum number of bytes to avoid monopoly of any single node. If more bytes are allowed, then other nodes may not get fair chance to send their data on the bus. Seventh and last field is the CRC of 4 bytes. This is mainly added by the Ethernet controller for error detection. Let us deep dive into different layers of OSI in detail and understand them starting from layer 1, that is the physical layer. The figure what you see in the right hand sides are the components of an ECU when we consider a physical layer. First one is a microcontroller, which is the host. This contains applications and basic software. The host needs Ethernet MAC for Ethernet communication. Next we have something called as Ethernet PHY, or we can also call it as Ethernet PHY. This is a hardware interface used as a transceiver module. The interface between the microcontroller and Ethernet PHY is called MII, which is Medium Independent Interface. We also have something called as Medium Dependent Interface, that is MDI, which is the connection between Ethernet PHY to physical medium. Here, physical medium means the actual physical cables used for the TX and RX. Some of the example of MDI are 100 base T1 or 100 base TX or 1000 base T, etc. We shall look into more details about it in few minutes in the coming slides. We also have few digital I/O connections for Ethernet PHY, which are SPI interfaces used for configuration of Ethernet PHY. I would like to specifically mention one thing here. All the figures or diagrams which I use in this video are available open source. Most of them are taken from the Vector Informatica website, which is available for reading to public as e-learning or webinar. Let's see different medium dependent interfaces available in market today. The first one is the 100 base T1, which was the initial version of PHY, which was also called as Open Alliance Broader Reach before it got the IEEE standard. It was developed by a company called as Broadcom. In 100 base T1, 100 means the bandwidth at which it can operate, that is 100 Mbps. T1 means single twisted pair of cable. This single twisted pair of cable can communicate both TX and RX message in the same pair of cable. Next one is the 100 base TX, which means 100 Mbps with two twisted pair of cable, as you can see in the diagram. So there will be dedicated pair of cable for each TX and RX. Next we have 1000 base T1 and 1000 base T, which operates at 1 gigabits per second, but the difference between them is that 1000 base T1 uses single twisted pair of cable and 1000 base T uses 4 twisted pair of cables for communication. This is a brief explanation about the Ethernet PHYs, but you must learn more about them. I must say it is very interesting and very important to know it in detail. Next let's see the layer 2, that is the data link layer. In this layer we configure MAC and VLAN. This layer defines basic function of communication. First is the bus access. As I stated before, the access control and the collision detection are the functionalities provided by this layer. It is also responsible to create a Ethernet frame which must have all the headers as we discussed before. It also responsible to state the type of node addressing. It can be unicast, multicast or broadcast message. There are certain values of MAC addresses which helps deciding the node addressing. Then it has something called LLC, which is logical link control. This field is used if layers higher than 2 is involved. It handles the connection of higher layers. Let's now understand how the communication at the data link layer happens. Consider 4 nodes connected over a switch. Each node has different MAC addresses. If this node 1 wants to send data to node 2, the Ethernet frame format will have the source MAC address of node 1 and destination MAC address, which will be the MAC ID of node 2. Then the switch routes the data to node 2 via data link layer based on the MAC addresses. This is how the Ethernet communication happens at the data link layer. If you notice one thing, an Ethernet switch routes the data based on the MAC addresses, so it is a device which operates at layer 2. Next is VLAN, which is called Virtual Local Area Network. The VLAN configurations are also done in data link layer. VLAN tags are used to group certain physical channels into virtual LAN. Let's say we group physical channels of node 1 and node 2 with VLAN 1 tag and node 3 and node 4 with VLAN 2 tag. Then the Ethernet frame will be added with this VLAN tag. As we see here, the VLAN type, which is represented by the value 0x8100, is the type of Ethernet frame to define it to be having VLAN tag, which is then followed with the VLAN ID. So whenever VLAN tag is added to the Ethernet frame, the switch gets to know that it has to be communicated within the VLAN network and will not go beyond the VLAN network. If we consider this example, if the message has to go from node 1 to node 2, first source and the destination MAC addresses will be matched. Then the VLAN tag will be checked. If it is set to VLAN 1, only then the switch sends the message to node 2. I have a question to the viewers here. So the question is, if I set the destination MAC address to FFFF, which is basically saying that it is a broadcast message and can be sent to all the nodes in the network, and if I set the VLAN tag to VLAN 1, then will the traffic cross the VLAN boundary and reach the VLAN 2 network or not? Give it a thought and let me know the answers in the comment section. Layer 3 is the network layer, which is also called as Internet Protocol layer. We have two types, which are IPv4 and IPv6. IPv4 is 4-byte addressing and IPv6 is 16-byte addressing. This layer allows routing of data across the network boundaries. Ethernet type will have the value 0x0800 for IPv4 and 0x86DD for IPv6. Let's compare and see difference between IPv4 and IPv6. Both of them have two fields within, which are network prefix and interface ID. By just looking at the examples of IPv4 and IPv6 addresses, IPv6 address looks more complicated and it is not easily readable when compared to IPv4 address. This is because the IPv4 address is a 32-bit address that comprises of binary digits separated by a dot, whereas IPv6 is a 128-bit address which is written in a group of 8 hexadecimal numbers separated by colon. There are different classes defined for IPv4 which are Class A, B, C, D and E, but IPv6 doesn't have any classes of IP addresses. Network prefix determines how many networks it can have, and interface ID determines how many hosts it can contain within that particular network. For example, for a Class A network, network prefix is 8-bit long, which means it can have maximum 127 networks. But as it has 24 bits of interface ID, it can have 16 million hosts for each network. So, class of IPv4 needs to be selected based on the need and application. If you have noticed or checked for the IPv4 settings of your PC, a Class C address is used, as Class C allows for approximately 2 million networks by using 24 bits of network prefix or ID. Here we can see the comparison of headers used for IPv4 and IPv6. IPv4 uses 20 bytes of header with lot of different fields or parameters information, whereas IPv6 uses 40 bytes of header, out of which 32 bytes are used for source and destination addresses alone. In IPv4, one main important header parameter which I would like to mention here is the PRT, which is protocol field. I will talk more about this parameter in a few minutes from now, but for a time being, let us just remember that data in this field gives information about the next layer. Also, this complete IPv4 header resides in the payload of Internet Protocol. So, when we spoke about the Internet Protocol, we saw source MAC address and destination MAC addresses. But here the source and destination addresses are IP addresses. Let us understand the network layer with an example. Let's consider network A and network B. If you see here, there are two ECUs connected over a switch which is grouped in network A and similar in network B. Let's say there are two ECUs within network A wants to communicate, then they could communicate over data link layer without using any network layer protocol. But that is not possible in case of communication between ECUs in network A and B, as they are not within the same network and are not connected to same switch. So when there is a need of communication between two different networks, they are differentiated using IP addresses, and IP addressing comes into picture. Let's come back to this example. As you can see, the ECUs in network A and B are of type C of IPv4 addressing, and ECU within a network has same network prefix and are differentiated with different interface IDs. For example, in network A, both ECUs has network prefix as 192.168.1 and interface IDs are different, which is 10 and 20 respectively. Similarly, the network prefix for network B is 192.168.2. Either of the networks has a possibility of having 254 different ECUs within the network. So, communication between two networks happens via the network layer, that is layer 3, with the help of a router. One good example for layer 3 communication would be the browsing internet at home via a router to access websites hosted in some other network. Layer 4 is the transport layer. TCP and UDP are the main protocols within layer 4. TCP is Transmission Control Protocol and UDP is User Datagram Protocol. Main difference between them is the way the communication happens. That is, TCP allows connection-oriented communication, whereas UDP allows connection-less communication. TCP mainly needs to have a transmission success or failure as feedback to the sender from receiver. But UDP doesn't need a feedback. It just sends the data and it is not concerned on how many receivers are present and whether the data is received or not. We will understand this in more detail in few minutes from now. In both the protocols, source and the destination ports are used for addressing. This is how a TCP and a UDP frame format looks like. You can see that there are a lot of parameters in TCP and very minimal in UDP. I just wanted to show how it looks like, so I will not go through in detail about the frame format in this video. Here we see the representation of different application with the ports defined, which communicates using these ports. For example, if application A wants to send data from source port 10,000 to destination port 20,000, the frame format will have these two port numbers mentioned or configured. From what we have learned so far, different headers of different layers of OSI are nested into the Ethernet frame format. Let's consider an example of UDP within IPv4. If we consider constructing an Ethernet frame for a sender message, the UDP header and the payload of the transport layer will be embedded within the IPv4 payload of the network layer. Similarly, the IPv4 header and the IPv4 payload, which has the UDP frame within, will be embedded as part of the MAC payload. This way, the complete Ethernet frame contains nested frames from all the above OSI layers. Now let us discuss in detail about the different application areas and how it looks like with respect to classic AUTOSAR. We shall also see which classic AUTOSAR modules are involved for different use cases and also touch on the data path too. First, let's discuss on the usual signal communication stack. This is similar to the conventional CAN communication but differs below PDUR layer. Let's consider a data to be sent on Ethernet. The data flow involves software component to RTE to COM, to PDUR, to SOAD, to TCP/IP, to Ethernet IF, to Ethernet modules. Socket adapter module can map it to layer 4 of OSI layer, which has configuration of ports or sockets which relates to TCP or UDP protocol. TCP/IP module can be mapped to layer 3 of OSI layer, which has configuration related to IPv4 and IPv6. Ethernet IF, Ethernet, Ethernet switch, and Ethernet transceiver can be related to layer 2 of OSI layer. In Ethernet IF module involves configuration of VLAN. Ethernet module involves configuration of MAC address of PHY. Second application is diagnostic over IP or DoIP. As the name says, the protocol is over the Internet Protocol. This basically lies between the layer 5 and 7 of OSI layer. When it comes to classic AUTOSAR modules, we have DoIP module which is below PDUR and above SOAD layer. This module is also available for bootloader. Third application area is one of the hot topics now when comes to service-oriented communication, that is SOMEIP. It is abbreviated as Scalable Service-Oriented Middleware over IP. As name suggests, this protocol lies between layer 5 and 7 of OSI layer. SOMEIP has two paths as shown in the figure. One is data path and another is control path. Control path involves the service discovery and involves configuration of SD module. In this module, we need to configure on different instance for a service event. It can be for both providing service or consuming service. Next is the data path, which involves configuration of some IPXF, which is within the RDE layer and SOAD layer. Part of some IP protocol is formed in some IPXF module, and other part of the protocol is appended in socket adapter module. Fourth use case is for the time-sensitive networking. This is directly over the Ethernet protocol, so it covers between layer 3 to 7 of OSI layer. TSN has different protocols like PTP, Precision Time Protocol, SRP, Stream Reservation Protocol, and AVTP, Audio Video Transport Protocol. That's all for this video. Let me know if there are any query on this topic in the comment section. I would love to answer those. Don't forget to hit a like button and also subscribe to my channel to be up to date with the upcoming videos on some other topic of automotive embedded system. Bye for now.